Your agent has been working for an hour, plan written, 3 files refactored, tests almost green. Then your laptop sleeps. The terminal closes. You come back, and it is gone. The plan, the progress, every step vanished. This is the difference between a demo agent and a production one. One survives, the other does not. Last video, we fixed memory, planning, subagents, skills, compaction, 4 mechanisms that keep your agent thinking clearly inside one session. But memory is not the same as persistence. Memory is what is in your head right now. Persistence is what is still there tomorrow. Production agents need both. So today we build the persistence layer. 2 mechanisms. 1, tasks stored on disk as a dependency graph, so the agent can crash, restart, and pick up exactly where it left off. 2, background operations. So the agent can run a slow build or a long test suite without sitting there blocked. By the end of this video, your agent does not just remember, it survives, and it multitasks. Most developers think they already have persistence. They use TodoWrite. The agent makes a list, it checks items off. Looks like state, right? TodoWrite lives in your conversation context. Same place as the model's working memory. Close the terminal, the list is gone. Compact the context. The list might get summarized into 1 sentence. It is a sticky note in the agent's hand. Useful for 1 minute, useless for 1 hour. So in January 2026, Claude Code shipped a different tool. It is called Tasks. And the difference is not the API. It is where the data lives. Tasks live on disk, specifically in a folder called .claude/tasks in your home directory. Not in your project, your home directory. That detail matters because it means the same task list survives across projects, across sessions, across crashes, even across reboots. TodoWrite was the agent's notepad. Tasks are the agent's wall. So how does it actually work? Tasks expose 4 tools: task create, task get, task update, task list. Same shape you would expect. Each task has a status: pending, in progress, completed, or blocked. And here is the part that turns a list into a graph. Every task can declare what blocks it. You call add blocked by with the IDs of tasks that have to finish first. The runtime stores the relationship symmetrically. If A blocks B, then B is blocked by A. You just defined a directed acyclic graph. Now the agent's algorithm becomes simple. Scan all tasks. Find every pending one whose blockers are all completed. Pick the next ready task. Do the work. Mark it complete. The completion automatically unblocks dependence. Loop. This is exactly how a task scheduler in any production build system works. The difference is, the worker is an LLM, and the graph survives every crash, because every state change is written to disk before the next one starts. Here is the part most tutorials never show you. Open 2 terminals. Both of them are Claude Code. Both of them are working on the same project. By default, they have separate task lists. They will fight each other. They will duplicate work. So Claude Code shipped 1 environment variable that fixes it, Claude Code task list ID. Set the same value in both terminals. Now both agents are looking at the same wall. When one of them claims a task, the ownership field locks it. The other terminal sees the change in real time because the file system broadcasts updates. So now you have 2 agents sharing 1 dependency graph. Without orchestration code, without a server, just a file path and an NVVAR. Tasks solve survival. They do not solve speed. Watch a default agent run a test suite. It calls the bash tool. It waits. 90 seconds of dead air. The agent cannot read a file. It cannot think. It cannot make a plan. It is a brain on hold. So Claude Code's bash tool exposes a single Boolean. Run in background, set to true. The shell process detaches into a daemon thread. The agent gets an instant confirmation. And then, and this is the elegant part, the agent does not poll. There is no while loop checking for completion. When the background task finishes, its result enters a notification queue. On the agent's next turn, it sees a system message. Background task completed. Exit code 1. 47 passed, 3 failed. The agent reads the failure, opens the relevant file, and goes to fix it. Meanwhile, while the tests were running, the agent was already reading source files. It was already drafting the fix. The 2 streams of work overlapped. Plus, there is one more lever, the timeout parameter, in milliseconds, so a runaway process never hangs the loop. Now combine them. This is the loop production agents actually run. Step 1. Pull the next ready task from the dependency graph. Step 2, start the slow work in the background, the build, the test, the deploy. Step 3, while the background runs, do the fast work. Read source files, sketch the next change, update the task to in progress. Step 4, the notification arrives, the background finished. Step 5, interpret the result, mark the task complete, or split the failure into a new task and link it back into the graph. Step 6, loop. Notice what just happened. The agent crashed yesterday. You restarted it this morning. It picked up at the next ready task. While it works on this one, the next build runs in parallel. 2 streams, 1 graph, 0 context loss. This is what production agent actually means. Now the honest part, both mechanisms have real edges. Tasks need explicit cleanup. If your agent crashes mid-update, you can end up with a task stuck in progress forever. The dependency graph trusts you to mark completion. Forget once and your wall locks. Background Bash has a known footgun. The Claude Code repo has open issues, 11,190, 11,716, where finished background processes spam infinite system reminders that exhaust the agent's context. The mechanism works. The lifecycle still has rough edges. The fix today is conservative. Use background mode for genuinely slow operations. Tests, builds, deploys, not for everything. The harness is real. It is not magic. Use it where it earns its weight. So that is sessions 7 and 8. Tasks turn the agent's work into a graph that survives every crash. Background Ops turn its bash tool into a parallel worker that lets it keep thinking. Together, a production loop that can run for hours, recover from failures, and coordinate across terminals. But here's the question that has been hiding under everything we built. We have one agent that survives. What happens when you have 5? In the next video, sessions 9 through 12, we close the loop. Agent teams, communication protocols, autonomous claim and execute, worktree isolation, the capstone of the entire course. If you want to be there when it drops, subscribe. The wall is built. Time to put more hands on it.